It turns out that we use definite integrals to help us find the area under a curve. And we kind of set this up by looking at rectangles, because those are easy area formulas. If I have a graph, maybe it looks something like this, and I want to find the area between some value of a and some value of b underneath this curve. I want to find that center area. Well, we don't really have a formula for that funky shape. But what I might do is draw a bunch of rectangles where maybe the left corner of the rectangle hits the graph. The problem is you'll notice that a lot of these rectangles don't quite fill the graph completely. There's a little bit of error in them. So what's the solution? More rectangles. If I had more rectangles, the error would be smaller and smaller. And it turns out if we get to the point where we use an infinite number of rectangles that are infinitely thin, we say they have a width of dx, some small amount, and a height that's equal to the function. And if we add up all those rectangles, that's like taking the integral from a to b. In other words, the integral from a to b of f of x dx finds the area underneath the curve. So for example, if I want to find the area under the graph f of x equals x e to the x squared plus 1 between x equals 0 and 1. Well, if we want the area under the function, what that means is we're going to integrate it from 0 to 1 of our function, x e to the x squared plus 1 dx. We can integrate this using u substitution, where u is the exponent x squared plus 1, and du is 2x dx, which means we're going to have to multiply by 2 and 1/2 to get all the pieces we want. Now we have 1/2 times the integral. Remember, we have to change these limits of integration by plugging them into the x in the u equation. 0 squared plus 1 is 1, and 1 squared plus 1 is 2. The 2x dx became my du, and my e to the stuff became just e to the u. And now we can evaluate this integral as 1/2 e to the u evaluated from 1 to 2, which means we have 1/2 e squared minus 1/2 e to the first power. And that technically is the area, or you can plug it into the calculator and get about 2.34 square units found under the curve between 0 and 1. This opens up the possibility to find many types of area formulas that we couldn't solve with our basic geometry formulas. In fact, if we want to find the area between two curves, it becomes even more powerful. And that's the topic of the next video.